Hello dear audiences, this is the Probability and Statistics for Engineer, episode 9. I am Mohammad Momenzadeh, the presenter of this lecture. Today we will discuss about the most important part of our discussion for the remaining parts of our course, which is the random variable and probability distribution function. So we state our definition in this lecture, and hopefully in the remaining part of the lectures we will discuss about the remaining parts. So first of all, let us take a look at the topics that we have. We have the random variable, probability distribution, discrete random variable and continuous random variables, and cumulative distribution and examples. So hopefully if we can finish this part, we will discuss about all of these things, and I think so that we can cover the discrete random variables today. So let us take a look at the slide for the random variables. So if you have a sample space, let me just sketch one sample space over here with one box. If we sketch the sample space and denote the sample space by the words S over there, then that statistical experiment contains some possible outcomes, and all possible outcomes can be drawn in the sample space as a sample points. For instance, if we toss a coin, for example, then we have two cases, the head and tail. And for these head and tail cases, we can define the events as a subset of a sample space. For example, this subset of a sample space, if we denote it by A, will be one type of the events. But always defining the events by the words and using some words to define it is not easy. It's impractical to define it. For example, to calculate the probability of A, first of all, I should define the events meticulously. And these things are not practical indeed, because we should explain it by the words and use a lot of things to talk about the probability of that event. Instead of that one, I define a numerical value and I correspond this h by one numerical values. In this way, it's easier to recall that type of the sample points. Indeed, I use one function, and in this way somehow I connect these sample points with one function that we call it the random variable. So over here I use x as a random variable, and this assigning the value is totally on my hand. It means that I can assign any values. For example, I can put -4 for x when x is denoted by head, and I can put 3 for the tail. I can use any numerical value based on the application of that things. Right now I use that numerical values over here, and as you can see, x as a random variable is a function. Indeed, this random variable is a function. It's not the variable by the meaning of the classical meaning of the random variable. You remember that when we discussed about the variable, it was the unknown things that we talk about it. But over here, this x, this random variable, determine a function. This function corresponding the numerical value for each sample points, and over here for head we have -4 and for tail we have 3. Right now, instead of talking the probability of A, instead of writing and determining that set and talking about the property of that event, I can simply write it as a probability of x equal to -4, because x -4 is totally as the same as getting head in our sample space. So the probability of x -4 right now, if the coin is unbiased, if the coin is fair, is equal to half, as you know, because we have two cases and occurring of each cases are as the same, has the same chances to be occurred over there. And instead of talking about, for example, probability of A complement or the complementary of A, which is the events that contains tail, I can use the probability of x equal to 3, and right now it's gonna be the half again. So in this way I can actually prepare a type of the graph for this type of the situation, and I can put them in one graph. Indeed, if I choose two lines, two axes over here, the y line determine the probability and the x line determine the variable, the random variable that we have it over there, then I can put all the probability over there as well. What does it mean? Let me just put one gap at the beginning to say that it's not started from 0 exactly. Then by this gap I determine that it's not started with 0, and I put the point -4 and then the point 3. And for these two values that I have it as a x, as a random variable, I can talk about the probability of x equal to xi as a y line. Right now we can put the probability of each value over there, means that I can put half over here. So the point over here is half and the point over here is half as well. We have two half values for them, and for this reason we can have this graph as well. So right now I have one type of the random variable, and over here we have the distribution function of that one, which is the next discussion that we have it. Let us take a look at the definition. A random variable that we denoted, abbreviated by RV, is a function that associates a real number with each element in the sample space, means that for each sample points we associate a real number. And how can we assign that values for the given sample points? Is totally on our hand, means that we can choose any numbers to determine the elements of sample space. Random variable will be denoted by uppercase letter. As you can see, I choose the uppercase letter. The x is an uppercase letter that we have it over here, and the value of that one, the value of the random variable or the observation can be determined by lowercase, means that the capital X equal to small xi determine the value of that random variable. So we have two types of the random variable. One of them is a discrete random variable, the another one is continuous random variable. But for the discrete random variable we have the following definition. A random variable is discrete if it can assume at most a finite or countably infinite number of possible values. So means that we can count the number of the elements in the sample space. For that cases we have the discrete random variable. We have some example for each cases, the discrete and continuous case, that we will discuss about it over here right now. Let us take a look on that examples. So we have the classical example of random variable over here. When two dice are tossed and we have the random variable over here as a sum of the score on the two dice. So it's important to understand that we can define any random variable based on our application. When two dice are tossed means that we have a sample space over here. If I want to just write the sample points, then I can write the sample space as well as follow. We have already talked about these cases before. So when two dice are tossed means that we have two empty places, and for each case we have 6 possibility, means that the number 1 up to 6 can be occurred over there, and totally based on multiplicative rule we have 36 cases. So these cases can be actually written in one line over here. So it's a bit long, but let us write it over here, the number that can be appeared over there in this statistical experiment. So here I listed all 36 cases that can be considered for tossing two dice. So you can see all cases over here. Right now, x is a sum of the score on the two dice. So it's very important to understand that we can define any random variable as I said it. For example, I can define another random variable. Let me just define y as a subtraction of two numbers that can be occurred over there. For example, if the first number denoted by x and the second one by z, then I can define the y as a absolute value or the differences between these two one. Then for each point over here, the random variable will be different. Let me just give a space for the second line and put it lower than that. So right now, as you remember that the random variable define the function, and the function can be defined in any way that we want it. So for instance, in this case that we have y equal to differences between the first flipping and the second flipping can be considered, and we have different actually cases over here. So let us return back to our question. In a question, as you can see, the x is defined as a sum of the score on the two dice. I want to emphasize again that it can be different and we can have the different cases over there, and it's totally can be determined based on a definition of x. For instance, for number 1 and 1, for the output of 1 and 1, we have 2 as the addition or summation of the scores. For 1 and 2, we have 3 as the addition of that numbers, and so on. We can do it for the remaining part as well. So as you can see, I complete that numbers and I determine the numerical value for each case of sample space, and we can denote this assigning of the number by x. So we can also put all of them in one table. As you can see, I just put them in one table, and you can see that with that table that I determined over here, the summation of two numbers are given. The first die and second die is determined here, and for each case I determine their addition inside of the table. I construct this table based on a random variable which is defined over here. At the end of the day, I can put all these values in one table, and I can construct a table that we call it the probability distribution function, or simply we can call it as a PDF. Means that in one row of that table I can put x equal to xi, the numerical value that can be considered for that case, x equal to xi for the first row, and for the second line or second row of that one we can consider the probability of that value. So means that the probability of x equal to xi, the capital S x or the uppercase x equal to lowercase x, the value of that one is given at the second line over there. So the first number that can be considered over here is a number 2. The addition of them can be a number 2, and if you take a look at the value that I just put it over here, I mean these values for the x, then you can see that only we have one cases of 2 over there when 1 and 1 is an output. So the probability, the corresponding probability will be 1 over 36. I can put the remained values over here and complete that table. Let me just complete that table as well. So we have this table that determines the probability of corresponding values, and you can see the probability of each cases over here. Moreover, when we have this type of the table, indeed we have the probability distribution function. This function determines the probability of each value over here, and based on that one we can calculate this probability. Moreover, we can construct one graph like the things that we did it before, and if we just construct this table, we can this type of the graph we can put the value of each probability on that graph as well. Means that we can put, for example, I just show one of them over here. So we have the output. Let me just put a gap at the beginning of that graph to say that it's not started exactly from 0. And then the first value that we have it over here is 2. This is the value for the x, or the random variable that we have it here. And the corresponding probability for that case is given over here by 1 over 36. Let us assume that this is 1 over 36. And this is the value that we have it here, 1 over 36. And the probability of each cases is given in a y line. Means that the probability of x equal to xi is given at the y line, and that vertical value determines the probability of each case. So we can complete that table as well, that graph as well. So I complete that table, that graph, and as you can see, the shape of this graph looks like a bell shape, and we will see this type of the figure in a probability too much. Indeed, this is the form of the normal distribution. Later on we will discuss about this type of the things. So based on this information that we can provide it from the given example, we can calculate the different probability as well. Right now, instead of talking about the events, we can talk about the probability of the value of x. For example, the value of x is equal to 5, means that I'm looking for the probability of an event that the random variable or the sum of the scores on 2 dice will be equal to 5. And as you can see, the only value that we have it here is 4 over 36. So this value will be 4 over 36. Moreover, we can talk about the range of the values for the random variable. For example, if I talk about the probability of x between, for example, 3 and 7, then we can calculate that value as well. Means that the probability of x between 3 and 7, for this case, I emphasize that I'm talking about this case, for the value of x between 3 and 7, and the equality is hold true for the 7, means that it contains some values inside of the table. It's not include the number 3, it's excluded, but the number 7 is included. So this part of a table should be added together to calculate that value. Means that this one is equal to the addition of the probability that we have it over there. Means that 3 plus 4 plus 5 plus 6, 3 over 36, plus the next one over there can be calculated as well. So we have these things. So you can see that the addition of these probabilities between 3 up to 6 over 36 is equal to 18 over 36, or half. And it's give you the information that the probability that the addition, the sum of the score on that case is between 3 and 7, and 3 excluded but 7 included, is equal to half. We can calculate this probability for the remained case as well, even for the cases that the probability is empty. For example, probability that the addition of a number over there, the sum of the scores over there, will be greater than 12, that one is equal to 0, because there is no value over there after 12. Means that after 12 we don't have any values. But if we change a situation a bit and put, for example, probability of x is greater than equal to 12, then 12 will be included in that case, and for this reason it will be equal to 1 over 36. Even we can calculate the complementary cases as well. For example, over here, if I just want to calculate the probability of x is less than equal to 12, then as you can see, this value is equal to 1 minus 0, or equal to 1. So means that I can calculate the complementary probability over here as well by using that inequalities. Or for this case, for example, the probability of x is smaller than, less than 12, then that one is not included, the 12, so the value over here will be equal to 1 minus 1 over 36 or 35 over 36. We can calculate that values as well by using this table. So again, as I said it, this table that I just sketched over here is denoted by PDF, the probability distribution function, and it's determined the value of the function of the probability over here and shows the probability of each point that we have it. So by the other words, I can summarize this information in one shape and determine the probability in one function over here as follow. So we can determine the given function by these values over here. As you can see over here, I define a function f over here. This function is related to the random variable x, the capital X. I denote it by f of x. At the point x, the small x over here, the given lowercase x, it's as the same as the probability of x at that point. Later on we will discuss about the definition of this probability distribution function or PDF, and as you can see, the value will be 1 over 36 for x equal to 2 and to 12, for 2 over 36 for the case that x is equal to 3 and 11, and at the end of the day 0 for the others. So we can define the function in this way. Let us take a look at the another example for the continuous case as well. So this is an example of a case that we have the continuous random variable. A computer randomly selected a number between 0 and 10. So for instance, the computer can select a number x over here. I want to emphasize that we tell you that the given value is a real number. This real number could be a pi, could be an irrational or rational number. There are infinitely many numbers between 0 and 10. It's not only 1, 2, or that type of the complete numbers or natural numbers that you know it. For example, between two numbers between 3 and 4, we have infinitely many values. We have a pi over here, we have 3.2 over here, then we have a lot of numbers. We have a Euler number e over here, some irrational like this, and some rational numbers as well. We have, for example, 1.4 over here as a one rational numbers here. We have infinitely many elements. Our sample space are infinitely, it's uncountable even. Our sample space is uncountable even over here. So if x denote a number over here, for example this number over here, then this random variable is continuous, it's not discrete, because you cannot distinguish between two values over here even. And when we discuss about the probability of something, for example the probability of selecting, for example, x as a number 1, this probability should be equal to 0, because 1 is only one number out of infinitely many numbers. The probability of x equal to, for example, 2, 3, 4, or even pi number is equal to 0, because we have only one number over here out of infinitely many cases. But talking about the interval has a meaning here. For example, the probability of x will be a number between 0 and 1. So it's going to be one interval. Right now I can talk about the interval of the values for the x. Then this probability will be 1 over 10, because as you can see, the probability of selecting one number, this segment between 0 and 1, can be considered as a 1 out of 10 segments that can be considered over here. Means that if I divide this sample space to 10 parts, as you can see, I just showed the division over here. We just asked to appearing of one segment out of 10 cases over here. Later on with the integral, we will discuss about these things. But right now, to understand the meaning, you can see that the probability of x between 0 and 1 is going to be 1 over 10. And more interesting part is about the border line over here. Again, if x, consider it as a value not equal to 0, only between 0 and 1, and if I remove that equality, then still that value will be 1 over 10. So means that in a continuous random variables, the adding a point or removing a point from the random variable does not affect the probability at the end of the day. And you can see that one by the property of the integral. I just determined this example to show you that what does it mean to have the continuous random variable. So right now it's a time to define the probability distribution function or probability mass function. We define this type of the thing as following: the set of ordered paired x and f of x means that we have the ordered paired here, that the first value determine the random variables value or sample points, and the second one over here determine the function f, which is the probability function, is a probability distribution function, or simply we use the PDF for that one. We abbreviate it with PDF, probability distribution function, or PMF, probability mass function. We use both of these abbreviation for this function. This is gonna be the probability distribution function if it satisfies these three conditions. First of all, this function should be positive, greater than equal to 0. Of course, the probability of a function should be greater than equal to 0. The second one, the probability, the addition of this probability should be equal to 1. Of course, the addition of that probability should be equal to 1, because based on an axiom of the probability, we know that the probability of sample space is equal to 1, and if I add all of this probability, the result should be equal to 1. And the third condition shows that the probability of x equal to uppercase x equal to lowercase x is as the same as f of x. We denote the probability distribution function by f, or we put the capital X at the bottom to emphasize about the random variable over here. So let us take a look at some example. So at this example we have three tables, and they ask you that to determine the table or the case that we have really have had a probability distribution function. Let us take a look at the first example. The first example give you some values for the x, and f of x or probability distribution function is given by the value at the second line. And based on a second condition that we had it, the addition of the probability should be equal to 1. But if you take a look over here, the addition of them, 0.3 plus 0.2 is 0.5, plus 0.3 is 0.8, and plus 0.2 is equal to 1, and the addition of them will be 1.1, means that the summation of the probabilities over there, the sum of f of x over here for the first case, is equal to 1.1. And based on these things, that the summation of them is equal to 1.1, the addition of them is equal to 1.1, then we can say that the first case is not the probability distribution function. For the second case, if you just take a look at the second case, the addition of them is equal to 1. As you can see, the summation of the value is equal to 1. But there is another problem here. What is the problem? Indeed, at the first item of the condition, we said that the probability values should be greater than 0. But over here, we have the probability value which is negative. Means that the g of y over here is negative. It's not greater than 0. It's less than 0 at the point 6. So at the point 6, that value is less than 0, and because of that, the second case is not the probability distribution function. Let us take a look at the last one. The summation of the value over here is equal to 1, means that it satisfies the second condition. For the first condition also, it's all of these values are positive. I just emphasize about these things, that the value of a function should be positive, not the random variable. Random variable are totally free, means that you can have the negative values over here or any numerical value, even the complex values. So when we have a negative value over here, it's not affect anything else. We just need to have the value greater than 0. look over here, I just emphasize about this one. We never said that x should be greater than 0. This is not a condition over here. So we just said that the value of the function or f of x should be positive, which is satisfied here. Moreover, the second condition is satisfied, and the last condition is determining the probability. All of them holds true for the last table. So the only case that we have a probability distribution function, the real probability distribution function over here, is the last case, and it's correct. Let us take a look at another example, and let us determine the probability distribution function with more complicated cases over here. So as you can see over here, we have a question, and in this question they told you that a committee of size 5 is to be selected at random from 3 chemists and 5 mathematicians. Means that we have a resource of humans over here. Let us put them in one bag to have more visual cases over here. We have for example 8 people over here. Let me denote the mathematician by the brown colors to not make a discrimination for them. I should put all of these mathematicians over here. So we have 5 mathematician over here and 3 chemists as well. So let me just put 3 chemists as well by the another color to distinguish between them. So we have 5 mathematician and 3 chemists over there. This is a resource of a people that we want to select a person or a committee from them. It's important to emphasize about the word of the committee. Means that a group of a people, then their order is not important. And if you remember from the counting part techniques, means that we should use a combination, not permutation. So I want to choose a committee of size 5, means that I need 5 person over there. So 1, 2, 3, and 4, and 5. We want to make a committee of size 5, and as I said it again, this is a committee, and when we have a committee means that their order is not important. By the another word, to use the counting cases, we need to calculate it by using the combination, not permutation. So we choose 5 person out of these resources, and I want to find the probability distribution function for some random variables. And this is important part, means that number of chemists on this committee determine the random variable, not the number of the mathematicians. The number of chemists over there in this committee that we have it is a random variable. So if I want to just sketch the table of the distribution, then this table of a distribution contains some values. So first of all, we determine the x. Okay, the x over here is a number of chemists. Is determined at the question. So x equal to xi determine the number of the chemists, and in the second line to determine the probability distribution function, we need to put f of x, or the function at the point xi, which is as the same as the probability of each point. Means that it's determined the probability of x equal to xi. So this is the second line value. So this is the probability of x equal to xi, and the number of the chemists in this committee could be 0, means that could be all of them will be mathematician, means that I can choose 5 mathematicians for making that committee. This number could be 1, or this number could be 2, or this number could be 3, but it cannot be any other values. So let us calculate the first value, means that the number of the chemists over there should be equal to 1. How? 0. How can we calculate it? So first of all, when we have a question, I said it before, that you should determine the sample space very well. You should understand the sample space very well. And if you understand it and knowing the number of the elements inside of the sample space, then you can solve that question. So then the sample space forms as a committee of size 5, all possible committee of size 5, and it can contains, for example, 3 chemists and 2 mathematicians, 2 chemists and 3 mathematicians, and so on. So because we select 5% out of 8 cases, this is 8 cases over here, to calculate the probability of x equal to 0. X equal to 0 means that have not any chemists inside of that committee. By the other words, we should choose 5% out of actually 5 mathematicians. So we have 5 mathematicians and we should choose 5% out of mathematician and 0% out of 3 chemists and multiply them by the combination rule. I want to emphasize that because it's a committee, we should use a combination, not the permutation. And total cases will be 5 out of 8 because we choose indeed 5% of a committee out of 8 resources over there. So it will be 5 out of 8. And we can calculate that one by using the permutation formula. So the permutation formula said that it's going to be 5 factorial over 5 factorial. And the differences between them will be 0 factorial. And of course 0 factorial is equal to 1. So the next one determine 3 factorial over 0 factorial again, and 3 minus 0 will be 3 factorial. And again, I want to emphasize that the 0 factorial is equal to 1, and denominator is 8 factorial, the number that we have it over there, over 5 factorial, and the differences between 8 and 5 is 3, so it will be 3 factorial. So we can calculate that one as well. The numerator is equal to 1, of course, because that 5 factorial and 5 factorial will be cancelled, and 3 factorial as well. For the numerator, we have 8 times 7 times 6 times 5 factorial, and 5 factorial is removed from there. And at the numerator, as I said, the 5 factorial cancel with that number at the numerator, and 3 times 2 times 1 is equal to 6 as well. After cancelling this value, it will be 1 over 56. 1 over 56 is the case that we have no chemist over there, and this value should be replaced here, 1 over 56. For the case that we have the probability of x equal to 1 as well, we have the similar things. Means that again we can say that the probability of x is equal to 1. Probability of x equal to 1. We should have the same thing. The denominator of that fraction is a combination of 5 out of 8, which is equal to 56 again. But for the numerator, we want to choose right now 4 mathematicians out of 5 persons inside of that group of people, and 1 out of 3 for the chemist as well. So again, 4 out of 5 will be 5, and 3 out of 1 is equal to 3. So we have 15 over 56. So the value that we have it for the next one is 15 over 56. And if I just calculate the remaining parts, let me just put it over here, you can see that the value that we have it are as follow. I mean, I can make that table simply like this, and for the remaining parts we have this calculation again, 1 over 56, 15 over 56 that we calculated. For 2 cases we have 2 out of 3 and 3 out of 5, which is equal to 30, and it will be for 2 cases is 30 over 56. And for the last case that we have 3 chemists, means that we have 3 out of 3 and 2 out of 5, which give you the 10 over 56. To examine your solution, always you can add these values to see that if the result is equal to 1 or not. If I add them together, let me just put the summation sign over here. You can see that 1 plus 15 is 25, plus 30 is 55, plus 10 is equal to the value that we want. It means that it's going to be 1 over there. So the addition of this value is equal to 1, or 56 over 56. It shows that the calculation over here is correct. So the another question that is remained is writing. Can we write the probability distribution function with one formula. Instead of writing them, we want to write it by one formula. For example, over here we can even use this form of a function to write f of x. We can rewrite f of x at the point x by the different values. Means that we can construct the function, the probability distribution function, as follow. We can say that, okay, we have 1 over 56, the value that we have it for the case that the x is equal to 0. For the case that x equal to 1, the value of a function is 15 over 56. Even we can sketch the function as well, plot that one in a two-dimensional space. So x equal to 1 over here, 30 over 56 is a value of a function at the point actually x equal to 2, and for x equal to 3 we have 10 over 56. So 10 over 56 for x equal to 3, and for the others, for the else where we have 0, so for the other value, for the others value we have, let me just write it, for the other means that if x is not equal to them, then the value is 0. The question is about that if we can rewrite this function by one formula. So indeed this calculation can be written as follow, means that we can rewrite it as follow, that the number of the elements, the denominator of that fraction is equal to 56. So let me just put 56 at the denominator. All of them has the same denominator, but the numerator is changed and is changed based on the value that we have it on x. So if you just take a look over here, we select x out of 3 over there because we have x values over there. So we select 2 out of 3, 3 out of 3, 0 out of 3, or 1 out of 3. So I can rewrite that value as a x out of 3, and this value determine the first combination parts. And for the second one, the number of the elements that we have it is a committee, and that committee is 5 minus x, means that we have 5 elements minus x that is selected out of 5%. So we can rewrite this formula like this for the x equal to 0, 1, 2, and 3. So for these 4 values over here, we can determine the formula of the probability distribution function by this fraction that you can see over there. So that's a case that we can rewrite them by one formula as well. Another topic that should be covered is a cumulative distribution. I leave this concept for the next lecture. At the next lecture we will discuss about the cumulative distribution, when the probability of a given function is gonna be the addition of the probability for the previous values, and we have some example that we will solve it in the next lecture. Thank you for your attention in this lecture.